Okay, so welcome back to our discussion on coding theory. The last code that we will discuss is the Hamming codes with error detection and error correction capabilities demonstrated using the nearest neighbor decoding. So to understand the Hamming codes, let's discuss what we mean by Hamming distance. The Hamming distance between two code words is the number of bits where the two words differ. If x and y are two code words, the Hamming distance is denoted by this symbol. Now let's demonstrate the Hamming distance using some examples. What is the Hamming distance between 0010 and 1100? Notice that these two code words differ in the first, second, and third bits. Therefore, the Hamming distance is 3. Let's try another one. What is the Hamming distance between 0111 and 1110? In this case, the two words differ in the first and the last bit. Therefore, the Hamming distance is 2. What about this one? What is the Hamming distance between 00100 and 00001? Please comment below for your answers. Now suppose that X is the intended message and Y is the message received. If there are no errors in the transmission, this means that X will be equal to Y. But we have mentioned previously that our channels are not perfect, and therefore there might be some errors in the message received. If there are errors, then X is not the same as Y. So the question is, how can we correct these errors and how can we recover the intended message? We will demonstrate it using the nearest neighbor decoding. So what is this nearest neighbor decoding? For the nearest neighbor decoding, the idea is to compute the Hamming distances between Y and each of the code words in C. In other words, we compute the Hamming distance of the received message to each and every valid code word in C. Now, in order to decode Y, we take the code word with minimum Hamming distance from the received message. If such a code word is unique, then we are able to decode the received message. If the distance between the closest code words in C is substantially larger than the number of bits errors made in the transmission, then this code word should be the received message. This means that if the closest code words or the closest valid code words has a distance that is larger than the number of errors made in transmission, then we can um, recover the intended message. This type of decoding is called the nearest neighbor decoding. So let's demonstrate this in an example. Suppose that our valid code words are these three, and suppose that the message received is this one. Obviously, there are errors because the message received is not among the valid messages. Now, let's decode this received word using the nearest neighbor decoding. So the idea is we will get the distance of y to each and every valid code word. So distance of y with this code word is 6. Hamming distance of y with the second code word is also 6. And then finally, Hamming distance of y with the third code word is 2. So let's demonstrate this in a diagram. Distance of y to this valid code word is 6. Distance of y to this valid code word is also 6, while distance of y to this valid code word is just 2. So using the principle of nearest neighbor decoding, this This received word will be decoded as this valid code word because this one is nearest to the received word compared to the other two. Now let's discuss how many errors can the nearest neighbor decoding detect and correct. In order to understand how many errors can the nearest neighbor decoding detect and correct, we discuss the minimum distance. The minimum distance of a code is the smallest distance between any two distinct words in the code. That is, we compute all possible distances and get the lowest of all those values. For example, if this is our code, we compute all possible distances. So we have distance 1, and distance 2. In this case, the lowest of all distances is 1. So in this case, the code has a minimum distance of 1. Now, what does the minimum distance do in relation to the how many errors can the nearest neighbor decoding detect and correct? So this is how we explain. Suppose that C is a code with minimum distance 2e plus 1. Then, it is possible to detect errors up to 2e bits. So meaning, if this is the minimum distance, our code can detect up to 2e bits of errors. And it can correct up to e bit errors. Let's try this on an example. Suppose that our code has a minimum distance of 15. So this means 2e plus 1 is equal to 15. Now, how many errors can this code detect? Okay. In our previous slide, we saw that it can detect up to 2e errors. So we solved for 2e and we found that 2e equals 14. So the answer to the first question is 14. Now, what about the number of errors can this code correct? So we saw from the previous slide that it can correct up to E errors. So to solve for E in this equation, we have E equals 7. So the answer to this question is 7. Let's try another example. Suppose that the minimum distance is 20. So that's 2E plus 1 equals 20. Now how many errors can this code detect? So to know the number of errors this code can detect, we solve for 2e. So in this case, 2e is equal to 19. Now what about the number of errors can this code correct? So in this case, the code can correct up to e errors. So solving for e, we have 9.5. However, 9.5 is not a valid answer. So we have to round down the number of bits into 9. So the answer to this question is 9. So this is a table representing the possible minimum distances and the number of errors it can detect and correct. So for instance, if the minimum distance is 3, then it can correct up to 2e errors, but can only correct up to 1 bit error. If the minimum distance is 5, that means it can detect up to 4-bit errors, but can only correct up to 2-bit errors. So this ends the discussion on error detection and error correction codes. For the next video, we will discuss the application of error correcting and error detecting codes.